and I will take away the screen sharing from you just for a second.
Of course. Yeah.
Yeah, hello everyone, and welcome to this week's EMinar. Today we have Raphael Rochlitz from LIAC talking about custEM from open source 3D modeling towards inversion. As always in the beginning, I just want to alert you to other EMinars that are going on in the next couple of weeks. So next week we have Simon Jowett on mining for net zero. So that's at the same time, and I think that's going to be very interesting, a little bit broader than the typical EM focus that we have here. And then in a couple of weeks, we have Sogi Kang, again, same time, 1400 UT, advancing Earth imaging techniques for improved understanding of groundwater systems. And the week after that, Gary Egbert is going to talk. Aaron told me he just got the information from Gary, so I don't have it on a slide yet, but you can find it online. Most of you will have seen this. There's the MTNet page where you can see the upcoming EMinars and the speaker way in advance. So if you want to know what's going on the next month, have a look there. And you can also see past videos and presentations that have been uploaded. So this is the definitive resource for all EMinars. And finally, just to remind everybody, please put your questions in the Q&A, not in the chat. So far, we've always done it at the end, and that has worked very well. I will monitor the chat and Q&A though, so if there's something urgent you want to ask at a certain point, I will tell Raphael that that is happening. And with that, I will hand over to you to share your screen and talk to us about EM modeling in Python.
Thank you, Max. So my screen is still visible, right?
Not right now. Right now,
oh, okay.
You.
Okay, so I will share again.
Now I can see you.
All right, now it should work. Okay, yeah, thank you for the nice introduction. Glad that I could give this EMinar talk today about 3D electromagnetic modeling with cusTEM, and also presenting our recent progress towards inverse modeling of CSEM data. I want to start with a short overview about our electromagnetic modeling and inverse model geometry. So I think we have two kinds of geometries. We have geometries with flat surfaces. For instance, on the left-hand side, we see the Dublin test model 1. Probably a few of you know it quite well. Here we have anomalies with rectangular shapes and transmitters, not transmitters, receivers on the surface, multiple observation lines in X and Y direction. And this is all with a flat surface. Another example would be on the right-hand side. So if we do not think about magnetotelluric modeling, but for instance, controlled source electromagnetics or transient electromagnetics, for instance, we can have a flat surface model with a dipole transmitter and an observation line perpendicular to the transmitter on the surface. Or we can also have a larger fixed loop. We can have a receiver array in the air or at the ground and some surface anomalies. But this is all with regular geometries. And for these geometries, we have a bunch of good codes which can handle these geometries very well. And they mainly use very preferable secondary field formulation technique to model and invert these setups. But this is not what I want to talk today. We have spent the efforts on implementing cusTEM for these more complex and real-world electromagnetic geometries. So for instance, on the left-hand side, we see a model which is in a coastal area. It involves a water layer, it involves bathymetry, it involves topography, multiple receiver stations on the mountains and the water with elongated transmitters. And specifically for our DESMEX project, semi-airborne measurements, there could be also an example with a land-based scenario with long, elongated and crooked transmitters in a mountainous area, multiple flight lines in the air, and strong topographic variation. So to handle these scenarios, we mainly focus on designing cusTEM. So before I continue, I want to give you a short overview about the content of my talk. I will continue with the motivation. After that, I want to present a couple of modeling examples. And the main part will be about our recent developments in CSEM data inversion. And finally, I want to give you some details about cusTEM, how to use it, where to download it, and something like that. When I started with this project, it was mainly part of my PhD until 2019. I did some extensive literature research, and I found that we have these multiple electromagnetic modeling disciplines. That means magnetotellurics, controlled source electromagnetics, and transient electromagnetics. And for these disciplines, we have different numerical methods, and the most popular ones are clearly integral equation, finite difference, finite volume, and finite element. And already in 2017, it was quite clear that the number of finite element codes was increasing, and it is increasing until now because of the possibility of unstructured tetrahedral grids to discretize areas with topography. I think this is the main reason why more and more people go for finite elements instead of other numerical methods. So, but if you think about our modern electromagnetic surveys and investigation areas, it is often the case that we do not only use one single method. So for instance, CSEM only or MT only. We also combine methods to investigate our geological targets. And this is, for instance, what we are doing in our DESMEX project. So everything started with semi-airborne electromagnetics. Here we basically deploy long dipole transmitters on the surface to get strong transmitter currents into the subsurface for a good signal to noise ratio. And to recover data from a huge flight area, we use helicopter towed magnetic field sensors. But this is not everything what we are doing. Meanwhile, in DESMEX, we also have lots of ground surveys. So for instance, long offset transient electromagnetics or magnetotellurics. Meanwhile, we are using also drones or UAVs for smaller scale setups, and also the so-called FEniCS method in the air. So we have multiple electromagnetic methods in the same area, and the question is, do we need separate codes, or would it be possible to combine these methods and the simulation and inversion requirements in a single software? So if we think in this manner about geophysical EM modeling, it involves, as I said already, magnetotellurics, controlled source electromagnetics, and transient electromagnetics. And all these methods have a bunch of functionalities which we require in common. So we need a numerical method for each of these geophysical disciplines. We need some kind of electric, magnetic, or potential field formulation of the Maxwell's equations. We can either go for total field formulations, which are more favorable for these topographic variation models, or we can go for secondary field formulations, which are clearly favorable for the flat surface models. We can use direct and iterative solvers to solve our remaining resulting linear systems of equations. And on the other hand, we have variations in the conductivity. Anisotropy can play a role, induced polarization can play a role. I already talked about this part. So in the end, it comes down to the discretization, which is relevant for all these geophysical disciplines. And it has, in my opinion, the strongest impact on the accuracy and the computational resources we require for our simulations and also for our inversion examples. And I thought about providing a similar table to the state of research in 2022, but it's pretty tough to fill such a table because we have way more publications in the most recent years, and with these way more publications, I think also the redundant content is increasing, and the impact of our individual developments is going down. And I think it is it makes sense that the availability, that means the number of open source development, increases considering this behavior of our publication strategies and development strategies. So this is just my view on the most recent developments. And I had a look on the MTNet page yesterday, and I thought, oops, maybe this is not up to date anymore, and we could work together on integrating all the new open source developments which have came up in the last years into this page. Just a short remark, because there are more and more open source developments, and this is just a bunch of codes I know, so there are probably way more out there, so please don't be mad at me if I haven't mentioned any code here. So very popular, of course, we have mod-EM for magnetotelluric, and I think also control source EM modeling. We have here WS-inf code, which is very often used. We have a comparatively new development from Alexander, which is available on request, I think. Where this is mainly for 3D MT modeling and inversion. When we have a broad range of 1D and 2D EM codes, meanwhile. But most relevant for my talk is this group of codes down here. So in the recent years, we have an increasing amount of 3D CSEM modeling codes, which are open source, and this is mainly what the group of Simpec is developing. When we have Dieter Wertmüller's EMG 3D code, we have Octavio Castellore's TetGen, and my own development. And we have also the PolyEM 3D software developed at the ERGM. And I'm quite happy that our development is part of a landscape of codes which is going more and more open source. And with that, I want to continue with the modeling we do in cusTEM. This is only one slide of equations to come back to our basic equations. So in cusTEM, in my PhD, I have implemented and tested many different electric, magnetic, and potential field formulations and approaches for finite element simulations. So this is kind of a summary of all existing formulations. But what we focus on meanwhile is mainly the total electric field formulation, because we can use this one for handling these topography or bathymetry scenarios by directly incorporating the source currents of our transmitters in the model domain. The alternative, I already mentioned it, are secondary field formulations. They are also available in cusTEM, but these are preferably used for flat surface geometries. And if you are interested in more details, I just want to refer to the publications about cusTEM in the last years. So let's start with a very simple half-space model to just get you a bit into the plots and ideas of forward modeling. So here we have a mesh, and in the center of the mesh, we have a short-directed, x-directed horizontal electric dipole source. When we have an observation line, you will see on the next slide with 100 stations. We calculate 4 frequencies in the range of 1 to 1000 Hertz, a very resistive airspace, a 100 ohm-meter subsurface, and we can get reference solutions for this half-space model by semi-airborne, semi-analytic codes, for instance, MPMod. And this is a zoom in the center of the area. So the observation line I will present later on is in an oblique direction to the dipole transmitter to not have a non-zero component. So all components are non-zero if we put the observation line in this oblique way. And what I want to emphasize with this simple model in the beginning is that in finite element analysis, we have 2 different, or not only 2, we have even more different orders of polynomial basis functions. So the higher the polynomial order is, the more accurate is the approximation of our Maxwell's equations in the end. And if we only use linear basis functions, we need very fine meshes with a very fine receiver refinement. For instance, in this scenario, I have built triangles around our receiver locations with 5 meter. Oh, no, not with 5, with 1 meter for the P1 computation. And for the P2 computation, I have refined my receiver locations only with triangles around them with an edge length of 20 meters. And also the overall mesh quality is a bit poorer than for the P1 computations. And this was already published a couple of times, but it's really important. That's why I want to show it again. So if we look on our observation line, for instance, on the horizontal magnetic field component, real part on the left side, imaginary part on the right side, we can see the curves for the 4 frequencies. And when we can add our custom results, which kind of fit very well if we only look at the amplitude plots. But if we want to look at the errors, we see some differences because this scale goes from 0 to 10%. So maximum error shown here is 10%. And this is the P1 computation on the fine mesh. The P2 computation on the coarse mesh goes with an error scale from 0 to 1%. So basically, if you compare the curves, we have about 1 order of magnitude more accurate results if we go for second order edge elements in finite element analysis. And this is what we are doing in all remaining examples, and I will present it. It's very beneficial to get accurate results with comparably less computational resources required as for P1. And yeah, I already told you this is just a short table to show you again what I mean. So we have meshes where the fine mesh has way more nodes. And if we calculate it with P1, we need a certain amount of RAM and a certain computation time. And it's barely the same for the P2 mesh. But as you have seen, the accuracy was way better with P2 computations. Before this plot has become very poor. So I'm sorry for that. Before I continue with a more complex scenario, I just want to point out that cusTEM was meanwhile used for different modeling examples and comparisons. And for instance, you can find a model with full anisotropy in a marine CSEM setup in Fei-Yang Wang's publication, which came out this year. If you want to see how it works with changes in the magnetic permeability, you could visit Paula Rulf's publication. And we have also implemented complex resistivities or better conductivities. So we can consider induced polarization effects, and we have validated our implementation so far only in 1D against MP-mod. And if you want to know more details about this, I've added some slides in the appendix. But what is more important, because I already talked in the beginning about it, I want to focus on real-world scenarios with complex geometries. And this is a very recent benchmark study, which was motivated by Dieter Wertmüller. So in 2019, Dieter came to Lindsay, to Octavio, and to me. And he asked us, would it be nice to compare this recently published large-scale resistivity model from Korea and MNSS. So this is an hydrocarbon deposit in east of Brasilia. And what we are comparing in the paper of Dieter are the electric field responses on 2 observation lines related to 1 receiver position. So in marine CSEM, we use the reciprocity principle. So the red lines are actually the transmitters, and the blue cross is 1 receiver location. How does a slice of a conductivity model provided by Korea and MNSS look like? It's shown on the left side. So basically, this model is about 6 kilometers deep, and it's like 30 kilometers large in X and Y directions, and at this depth we have a hydrocarbon deposit. And the challenge now is, because the conductivity model is provided on a regular grid, to transport or to interpolate these resistivities on an unstructured grid. And this is a bit of a tricky situation, because actually we have an irregular geometry, but the basic information we can use for our benchmarking with custEM is provided on a regular grid. So that's a bit tricky. Anyway, we have also some information from seismic data. So we know the depth of the main geological horizons, and we can include these geological horizons into a mesh. So we have a kind of a good approximation of the main geological horizons, and that also helps us to interpolate our resistivities later on, because the main geological horizons have kind of phases to the next element. So that makes sense. And one message. It's not done. Okay. We can interpolate the resistivities in the central part of our model. And in order to reduce the boundary effects, I appended a boundary mesh, and I extrapolate the resistivity values on the edges of our original resistivity model. And now I want to show you some results of a comparison. So this is published by Dieter in 2021. We have a EMG 3D code, we have the custom code, we have a TetGen code, and the SIMPAC code, and every one of us tried to reproduce the results published by Korea and MNSS. And if we look at the curves, we see that basically all our codes produce results in the same error range. So it's basically less than 10%, which is okay, but not awesome. And we also see that the SIMPAC and EMG 3D codes kind of fit a bit better to each other, or show a more similar behavior than the unstructured tetrahedral discretization used for custom TetGen. We also see that Octavio's and my results are quite similar. As you see, the misfit is kind of less than 0.1% between our codes, and this is due to the fact that we used the same discretization. So if our implementation of a numerical method is correct, that's the point. It comes down to discretization, and if we have the same discretization, we get the same result with different codes. The challenge is to discretize our model correctly and to get results less than 1%. I think it would be a tough work and a tough challenge to work further on this example and see if it is even possible. Yeah. So this is one of the complex scenarios we had so far. Now I want to present one example of time domain modeling and one example of magnetotelluric modeling. For time domain modeling, we implemented 3 different numerical approaches in 2020. This was published last year. So basically we can use frequency domain calculations and fast-Hankel transformations to get our time domain responses. We can use the implicit Euler method. So this is a time stepping approach. And we have also Krylov subspace methods. So in this case, we consider the rational Arnoldi method published by Ralph Uwe Börner before. The example we used for the comparison here is a 3D model, which looks kind of a bit similar to the Dublin test model. We have 3 different anomalies in the subsurface, 1 kilometer long dipole transmitter. We have 3 observation lines with each 6 stations. And the anomalies have, 2 are conductive, 1 is resistive in a half space of 100 ohm meters. And the overall dimensions are something like 6 versus 4 kilometers. So this is a kind of low-tem scale model for the comparison of our time domain methods. And to validate our implementation, we compared our results with a SLDMEM software developed by Truskin and Knieschnermann, and which is still available at the University of Cologne. And we see that our results, so this is 1 receiver station in the lower left corner above anomalies, the BZ derivative in nanotesla per second. We see the transient from 100 microseconds to 1 second, and in black the SLDMEM solution, and colored the 3 different custom simulations. So the implicit Euler method, the Fourier transform-based method, and the rational Arnoldi method. And if we look at the errors for this comparison, we see that the Fourier transform and the rational Arnoldi methods show kind of similar errors. So here it is mainly a matter of interpolation errors, I think, and discretization. And the implicit Euler method involves also another error source. This is the time stepping. So if you choose a different time stepping, this of course affects also our errors, but basically this is a proof of concept that our implementation of all 3 methods is correct because we have compared it with a real 3D model. The interesting point is the Fourier transform based methods require most time because we need to calculate for not hundreds, but tens of frequencies. This really depends on the number of filter coefficients for the fast-Hankel transformation. This one can be probably reduced down to 30 or something if we optimize it, but it would be still kind of the most time-consuming method. The implicit Euler method is a bit faster, but it also depends on the time stepping. So if we use smaller time steps, of course, we need more computations, and then the computation time increases. And the rational Arnoldi method is just super fast. That's everything I want to say. It's a very nice method for time domain simulations, and it's nice to have it available. So thanks at Ralph Uwe at this point for helping me implementing this method into cusTEM. Now I want to come to the magnetotelluric example. So it stands to reason that I thought about validating my implementation with the Dublin test model because we have already multiple reference solutions available on MTNet. You probably know this large-scale magnetotelluric model quite well with 3 different anomalies in the subsurface. And I will show you just some results on this wide x-directed observation line. So these are my results for the 0.5 Hertz frequency on the left-hand side, apparent resistivity on the right-hand side, the phase. We have off-diagonal components and we have a main diagonal component. And I compare my solutions against the one from Maggie and the one from Han and Lee. So against a finite different and a finite element code. And what we see if we look at the errors down here, so errors for the apparent resistivities and errors for the phases, is that the custom solutions are in a very similar misfit or mismatch range when the two other codes compared with each other. And we also see that the custom solution kind of is more, shows less mismatches or less errors against the Han and Lee solution, which is also a finite element discretization than the finite difference method. And yeah, I think this is another argument for the fact that discretization matters to kind of get one or another result. To sum up the part of 3D electromagnetic modeling, a very particular point is that all these computations I have shown were computed with a direct solver MUMS. So MUMS is very robust, MUMS is nice, but MUMS requires lots of RAM. So we need hundreds of gigabytes for our simulations. And when it comes to inversion, we need even more gigabytes of RAMs. So we have some iterative solvers for finite element codes, for instance, published by Alexander Greiver or Vladimir Putsirev, and also others, but they are all for secondary field approaches. And for this total E-field formulation, there is no iterative solver. At least I don't know any iterative solver. And with an iterative solver, we can bring down the RAM cost. So that would be a nice feature for the community if someone is able to find a nice combination of preconditioners and iterative solvers for these ill-conditioned systems of equations. Another point, more general, of course, Marlim has shown that we have errors less than 10%, but not less than 1%. And also, if we look at the Dublin test model comparisons and others, we often have mismatches of more than 1% of error if we compare our codes against each other. And I think this is not really satisfying. So maybe we can continue with further benchmark models and trying to go more into detail to really analyze the reasons for our modeling errors. And the last point, I think that most of our community models or benchmark models that exist are not really suited for benchmarking the unstructured grid codes implemented for topography models. So it makes not, of course, custom is not better suited, for instance, for the Dublin test model or this low-TEM model I have shown you, because it's a flat surface model with brick-like anomalies. So all the other codes are kind of preferable with secondary field approaches. We do not need unstructured measures for these kind of models. We need to use our unstructured grid codes for models with topography and bathymetry for benchmarking. This is my view on the things. All right. Now, enough with forward modeling. I want to continue with real data and data inversion. So my PhD thesis and also my current employment is part of a DESMEX project, deep electromagnetic sounding for minimal exploration. I already mentioned in the beginning that we are using a mainly semi-airborne methods to find mineral resources in great depth. So surface transmitters, helicopter towed receivers. And this is an example from our measurements in Kiruna in 2018, I think. So a big ore mine. We also have conducted several measurements in Germany, and meanwhile 3 different main target areas, but also some further test sites. Yeah, this is what we are collecting. Yeah, these are the kind of data we are collecting in the DESMEX project and which we want to invert with cusTEM now. For the inversion, we use the pyGIMLi inversion framework published by Brücker et al. And this pyGIMLi framework uses a Gauss-Newton minimization scheme. And in this Gauss-Newton scheme, we basically need to provide the forward operator and the Jacobian with custEM, because pyGIMLi deals with a complete inversion procedure. So pyGIMLi has the inversion framework implemented, and what we can do is we can set our own modeling base, we can set our own forward operator, which is custEM, which is already existing, and we of course need to get the sensitivities for our inversion, and this is what we were implementing in the last year. So going not only for forward modeling responses, but also for sensitivities. And we decided to use the explicit sensitivity calculation procedure, as for instance published by Rody, Egbert and Kelbert, Alexander Greiver, or Feyang Wang. So we have a data Jacobian, and each entry of a data Jacobian is a derivative of each data point or each observation for each after each model parameter for n observations and m model parameters. We do it in a similar manner as Alexander. So we split our complete Jacobian into sub-Jacobians for each frequency. So for instance, this can be 10 or 12 sub-Jacobians in our current analysis. And each of these sub-Jacobians is a combination of electric and magnetic field observations. So in semi-airborne, of course, most of our observations are magnetic field observations in the air, but it can be also electric field observations on the surface. And each of these sub-Jacobians consists of 2 for real and imaginary parts times the number of observations times the number of sources entries. So this is basically the structure of our Jacobian. And to calculate these entries explicitly, we can map our electric or magnetic field observation in terms of H or B with interpolation matrices. So to get our data from the complete model solution, we can formulate these explicit interpolation matrices, and with this Q, we can write our Jacobian as follows with a vector G, which consists of derivations of a total field solution after the model parameters. And with a so-called reciprocity trick, we do not solve this system of equations for the number of model parameters. We can solve it with post system of equations for the number of observations, which is usually less than the number of model parameters. So we save some time because we need less solutions of right-hand sides. And what I also need to mention is this procedure is favorable for direct solver codes because we only need one system matrix factorization, which we already have if we calculate forward responses. And each calculation for each row of a Jacobian is only a back substitution with an already factorized system matrix, which requires only a few seconds time or even less. So basically these back substitutions are quite cheap compared to solving the forward problem, and that's why this method is favorable for custEM. We have implemented 2 different types of inversions so far. So first thing would be 2.5D inversion with a 3D forward modeling mesh, but with a 3D forward modeling mesh, but a 2D inversion mesh. So we add some prisms in our half space. Can be also a topography on the prisms. And if we think about an observation line oblique to a surface transmitter, like in a low-TEM scenario or a low-TEM geometry or a single flight line in our semi-airborne measurements, this is a probably quite reasonable setup for inversion because we have only 2-dimensional inversion on a line. And we can also compare our results with an established Mare 2D EM code directly if we have an option of 2.5D inversion. The other thing, of course, is 3D inversion. So for 3D inversion, if we consider a certain mountainous area, like shown in the beginning, with our transmitters and receivers. We built an inner inversion area shown in blue here with 5 cells, and each cell is a model parameter. So our inversion model has as many model parameters as there are cells in this inner domain, and also around the inner domain shown in the less transparent edges here, an outer inversion domain to kind of let the conductivities fade out until they reach the half-space model. So this is, we tested some things, and this is a quite reasonable setup for discretizing our inversion mesh. And of course, in the center of our inversion mesh, we will have transmitters, and we have our airborne electromagnetic field receivers. And this model is exactly what I will use now to do a first synthetic inversion benchmark. So on the left-hand side, we have the same geometry as shown in the inversion model before, but here you see the model I used for calculating the synthetic data. So I added 4 anomalies beneath our flight areas. From the left to the right, we have 5,000 ohm meter, a very thin anomaly, which is highly conductive, a larger dike with 50 ohm meters, and everything is located in the 500 ohm meter half space. And the amount of data are 4 times 220 receiver stations for each transmitter. So we have 4 transmitters, and each transmitter has 220 observation points with all 3 magnetic field components. And in addition, it's hard to see, but we have also some single dots here. These are receiver stations where we record electric fields on the ground. And these stations record from all transmitters. We are inverting for 12 frequencies between 6 and 3,500 Hertz, which is also the frequency range of our real survey data. And we added a Gaussian noise of 5%, which is quite typical for synthetic inversion tests. And our inverse model consists of 63K data points or observations in total for all frequencies, and roughly 100K model parameters. So this is kind of a larger scale inversion setup here. Okay, and now I want to show you the results. If we include the real topography in our inversion mesh, and as you can see on the first view, it looks quite nice. So we have a resistive anomaly here. We have a highly conductive anomaly where it should be, a less conductive anomaly where it should be, reaching until the surface, and also this flat brick with a smallest conductivity contrast is kind of resolved. I mean, not that sharp because the contrast is not that high. So this is kind of expectable, and we have also a nice convergence of our inversion model. And I was curious about what happens if I do not consider the real topography, but invert my synthetic data with a flat surface. And this is shown on the right side. So it's the same data set, but we use an inversion mesh with a flat averaged topography, so a constant z height for the surface. And we can already see in this example that we have, we see the main anomalies, that's true, but we also see lots of artifacts in our inversion model, and in particular on the surface. And also the convergence was not that sufficient in that case. So we cannot fit our data with a flat geometry. That's what this number indicates, in my opinion. And to go a bit more into detail, I will show you now surfaces of anomaly, which include areas of the inverse model, of a resistivity model with a certain resistivity range. So here, let's start with very high conductivities, low resistivities from 10 to 50 ohm meter. So basically, this should these areas should mainly occur in the highly conductive thin plate and also in the larger dike. So this looks reasonable in our real topography synthetic inversion, but in the flat topography inversion, we already see that the range is not covering the anomalies so well, and we also see first artifacts. And now we will see 2-3 further slices. So this is the range until 100 ohm meters. So of course the volumes increase in shape because we have now higher resistivity values involved. But we see in the real topography inversion, oh, okay, it's still nice. So we only see areas where our anomalies are really located, whereas in the flat topography inversion, we see even more artifacts and also an artifact in the anomaly, which is which is only 200 ohm meter. So continuing further until 250 ohm meter. Yes, we have also the less conductive brick now involved in our view. And in the flat topography inversion, we see even more artifacts, mainly on the surface, but also kind of larger volume down here. And this is in about 500 to 1 kilometer depth with, let's say, 200, 250 ohm meters. Compared to the rest of the model, this is a conductor which we possibly could misinterpret as a minimal deficit or something like that. So I think this example shows quite well that considering the real topography for our semi-airborne data and also other scenarios with topography is really important. Last slide I forgot to show. If we look also at the resistive body, so we add resistivity is larger than 2000 ohm meter, we can see that it is very well resolved again in the real topography inversion, but not in the flat topography model, even more artifacts. So this is yeah, one test I wanted to show you. Now let's come to a real data example. This is from the Schleiz area. So we conducted many surveys in the in this area in Germany, which is the Berger anticline. So we have different Ordovician, Silurian, and Carboniferous rocks here, which with lots of faults and folds. So this is a quite complex geological area, and we did semi-airborne measurements in this red area here in the years of 2016 and 17. The good thing is we already have some reference data available from pure airborne EM measurements conducted with a resolve system. So we have a kind of good resistivity model on the surface available for referencing our results and for seeing where we want to place our flight areas. And first data of our semi-airborne experiments were published by Maria Smirnova in 2019. After that, we have Michael Becken has updated the processing. So we have a kind of optimized processing algorithm for our data now. And with this, some data, some 2D inversion data are also included in Annika Steuer's publication in 2020, who compares different electromagnetic methods on a profile in our area. So this is the red area you've seen before. It has an extension of, I think it's like 40 times 10 kilometers or something like that. So this is the overall extent. We have multiple flight areas of semi-airborne data, but on this blue long profile, we have also ground measurements. And this is mainly a large-scale geoelectric survey, so ERP, inverted in 2D. On this profile, we have also a large-scale loading survey conducted with Mare 2D, inverted with Mare 2D EM, I think. And we have also inverted flight lines on this long profile with Mare 2D EM. So these are all 2D or 2.5D inversions. And what we basically see is that, yeah, the big red blob, let's call it like that, is always visible, but the structure of this big red blob is not identical. So we already see some differences for the different EM methods in our inversion results. Yeah, I think that's reason to go back to this area and see what our 3D inversion can do here. And of course, it's also a good reference for our 3D inversion of real data. So now we pick only 4 flight lines on the left part. Let's go back to the map. So we are considering this part of a geological map and this part of a profile, so the left side of the profile now. This is the length of the flight lines here, and the two transmitters TX1 and TX2. So with the two transmitters, you can see where we are. And these are the data on the 4 flight lines. So these are transfer functions, the magnetic field scaled by the source current of our transmitters. We look at the frequency of 31 Hertz here. So this is the second lowest frequency I think we invert for. And these are the data for the transmitter 1. So for this one, and down here we have the data for the transmitter 2. On the left-hand side, we have an X component. So we rotate our data to a coordinate system where our flight lines go in X direction. So that we have basically not really a Y component. And we invert this TX data and TZ data combined. And we invert also both transmitters combined. So this is the data set over multiple frequencies up to 1000 Hertz, which go into our inversion. And yeah, I already told it, we use 10 frequencies between 22 and roughly 1000 Hertz. And we use an error model of 5% plus 1.5 picotesla per ampere noise. And the Mare 2D EM versions, I used to compare my custom 3D results provided by Michael Becken here. So I just wanted to mention it. And we have 4 flight lines from top to bottom. We have a model with overall 1 kilometer depth. The length of this profile is 7 kilometers. And we see that, we have a varying 2D inversion result and a less varying 3D inversion result. That's kind of interesting. And something else we see is that the left side of our inversion result is quite similar in 3D inversion and 2D inversion. So I think this is very well comparable. But the right side is not so comparable. So we see clear differences in the shape and structure of this big red blob, if you want to call it like that. This is a big black shade conductor we can also see in the geological map. And to further investigate these differences, I have also conducted a 2.5D inversion with cusTEM for this flight line 7, which is the closest one to our long profile. And if we compare the Mare 2D EM inversions with our cusTEM inversions, we suddenly see that the right side of our resistivity model is very similar to the Mare result. So my conclusion here is that this is probably related to the nature of 2.5D inversion of 3D data in a 3D environment. So we have a difference here, but actually this is rather a result of regularization because our data only go until here. So this is not really significant. More significant is the structure in this area, which is very well covered by our data. And we also see that our 2.5D inversion converges not so nicely than our 3D inversion. So probably the 2.5D inversion has more issues to find a reasonable resistivity model for our 3D data. And this becomes also more clear, I think, if we look at the 3D inversion result for the 4 flight lines. So we see in the left side that our 3D model is also more two-dimensional regarding the resistivity structure, and this fits well to the more 2D structure of real geology. So here we have again some black shales, which are the conductive anomalies in our inverse models. And on the right-hand side, we see some black shales here, but we also see a fault approaching and coming closer to our profile and some other rocks here. So this is more like a 3D geology, which we already know from our geological map. And considering this and also the 3D inversion result, we see that if our geometry becomes more 3D, it is probably more reasonable to do a 3D inversion than 2.5D inversions on flight lines. And this is the motivation to really go for this 3D inversion approach with cusTEM. So now you probably want to know how expensive these custom inversions are. And these are just the numbers for the two models I've shown you. So the synthetic model is quite large. It has more nodes than the Schleitz model because this was only a subset of a flight area. I used 60 cores in both cases. The computation time was almost 2 days for the synthetic model with like more than 5 hours per iteration. But it was also a very large data set with more than 5,000 observations per frequency. And the point here is, and this is probably different to previous inversion tools, that our forward computation time is not the bottleneck. The bottleneck are the back substitutions, because we have so many observations that even a few seconds per back substitution sum up to a couple of hours. And we have also, of course, an increased time for the inverse solver, because the inverse problem is significantly larger in our synthetic case than in the real Schleitz case here. So a few further facts, I already told you. So back substitution matters really in our inversion approach so far. The 2.5D inversion is currently an algebra overhead, which I need to fix. Because right now it required more time actually than the 3D inversion. So this should not be the case, and this can be resolved. And the inversion times of the inverse problem could be also potentially reduced if inverse solver in pyGIMLi can be parallelized. So this is something I need to discuss with Thomas if we can save some time here. To sum up, we want to continue our implementation of an inversion framework. We need to work on better error models for our inversions and for our semi-airborne data sets. We want to use, because we have it, the explicit Jacobians for resolution analysis, and also capabilities for combined inversion of EM data sets. So for instance, combined MT and CSEM. I have a few options in mind to speed up the inversion procedure to handle even larger data sets in kind of a few days. We could also think about different inversion strategies, of course. And in the end, we also want to provide, similar to our modeling examples, these inversion examples to the EM community. And with that, let's talk about cusTEM. This is just, again, an overview what cusTEM does. So cusTEM involves mesh discretization. cusTEM involves finite element analysis and assembly of system matrices. And cusTEM involves the solution of our finite element systems and different post-processing capabilities. And cusTEM relies mainly on the FEniCS project. This is an open source finite element algebra package. We rely on pyGIMLi and TetGen for mesh generation, and pyGIMLi now also for inversion. The commit toolbox for our primary field solutions and the secondary field formulations. And we rely on PETSI and MUMS for parallelized algebra and solution of the system of equations. If you want to find information about cusTEM, just visit the Read the Docs page, which I updated in the beginning of March. There's also a new cusTEM version I provided at the beginning of March, because we have had quite some development progress in the last months. And if you want to access the source code, I would ask you to visit my GitLab page with the cusTEM project. You can also access different examples for forward modeling. So most examples are for frequency domain EM. There's one MT example, there are 3 time domain examples. Could be more, but it also costs some time to maintain and provide these examples. So if someone is interested, we can probably also add even more examples here with further comparisons. And these examples can be accessed also from the GitLab page. If you want to install cusTEM, it's pretty simple. You can just read the installation instructions, and if you install the Anaconda environment on your Unix system, you can install custom simply with this command line. So there's an environment package which installs all the dependencies and the Python source code. And you would probably also like to know what computational resources are required for different problems. So simpler toy problems, like the first example with a horizontal electric dipole and for observation and for some tests, can be easily run on a desktop machine with 4 cores and 32 GB RAM, which is kind of standard. Meanwhile, I don't know. But for serious modeling studies, you need some kind of a smaller workstation with at least 16 cores and 128 GB RAM. And for the real-world problems and the large 3D inversions, you need like more than 60 cores and 1 TB RAM. That's what I would suggest. So yeah, I forgot to mention. So the largest inversion, the larger synthetic inversion required 1.2 TB RAM for calculating 12 frequencies in parallel. So yeah, this is the amount of RAM I required so far. Finally, a few notes about the code handling in custom. So there is no GUI or something like that, but we have tried to provide many functions that simplify the different tasks. And this is just an overview about the code, which a code for generating a mesh could look like this. We need to define some transmitters, for instance, a dipole transmitter with 20 segments and an additional loop transmitter. And we can add our refinement triangles to our mesh. We basically build an empty word in the beginning, which is the blank world with a name. And after that, we can add the surface mesh, which can include transmitters and receivers. Then we extend our 2D mesh into 3D as a half space or a layered earth. And after that, we can also add some anomalies like bricks and plates or inversion domains in our mesh. So this is basically the extent of a mesh generation code. And for running our simulations, preferably in parallel with MPI run syntax, modeling code could look like this. So we need to initialize a modeling class. And the interesting point is here. So the approach determines the method. Basically, most of the other things do not change. We exchange our total electric field formulation with an MT approach. We are getting an MT solution for the same model geometry. So this is what I meant with combining the different methods in a single environment. Yeah, other things are defining model parameters like frequencies and conductivities, the finite element stuff, and the solution process is very automated. And at the end, we can interpolate our results wherever we like. Now, this is a last slide to show the code handling for inversion. So basically, we can import some data, in this case, semi-airborne electromagnetic data in a certain format. And after we imported the data, we can build a mesh. And in this mesh, we need to include the inversion domains as shown before with prisms or areas of cells. And after that, we set up our forward operator. So I designed this multi-forward modeling class, which uses parallel custom forward modelings at the same time for the different frequencies. So if we have 10 frequencies, we can calculate all these frequencies at once with this multi-forward modeling class. And yeah, we provide this forward operator to the pyGIMLi inversion framework when we could set a data transformation. In our case, this trans-symlog transformation is reasonable for the EM data with log scales and different signs. And finally, we run our inversion with pyGIMLi. So this is how the code looks like in the moment. So what is the outlook for custom? So actually, custom is mainly a work of my of me in the last years, and I think it could be reasonable to make custom independent of me. So I don't know what I'm doing in the next years, but I think it's a nice project. And if others are involved and if we can share responsibilities for the developing, maybe this code can be useful for the community also in a couple of years. And in that manner, it would be also nice to implement some more features like iterative solvers or adaptive refinement. At some point, custom needs to be transitioned to the new FEniCS environment. So FEniCS is not longer supported. It works fine, but there will be a better environment with more features and yeah, most recent algebra packages and stuff like that. So it makes really sense to transition custom to FEniCS. And we could also think about getting funding for sustainable software developments with the current state of custom, I think. Okay, and finally, I just want to comment on some arguments for open source. I think it is very reasonable to go for open source because it simplifies the access to others. It is guaranteed reproducible. We have less redundant developments. We have more innovation, and it is also easier to debug problems or issues if someone points with a finger on them. And just a personal perspective from me as a kind of younger scientist in a postdoc phase, I think going for open source really simplifies networking. So I got to know many nice people from the EM community over the past years in Germany, in Europe, and all over the world. So I think it is really nice to share some knowledge, share some modelings, benchmark different solutions. And in that manner, I want to thank you for your listening. I want to acknowledge a couple of people which helped me implementing all the features in custom and which did modeling studies with me and discussions. And yeah, now I'm ready to answer your questions. Thank you.
Thank you very much, Raphael. That was very interesting. And yes, certainly I mirror your remarks about open source. I think it really can, or it helps to transform also the research landscape. So please, everybody, start typing your questions in the Q&A. Actually, I'll start with a very basic one in the very beginning. So you were talking about the polynomial degree of your finite elements, and you said, okay, one, is sort of the standard one, and you need to have this fine meshes. Then two, you get away with coarser meshes. The computational and memory time is the same, but you get higher precision. Yes, I understood that correctly.
Exactly.
And then the question would be, so why not continue? Why not go to 3, 4, 5? I mean, those exist, right?
Yeah, that's a very good question. So third order polynomials were used by Alexander Greiver and Octavio Castillo-Reis in TetGen, as far as I know. So probably someone else also investigated on this, but Alexander and Vladimir and Octavio both found that P2 is kind of the best compromise between accuracy and performance. So the problem is that our system matrices are not that sparse anymore with higher order polynomials. So if we go for third order, actually I have a table in the appendix for the moment. This one, exactly. So if we go for third order polynomials, the sparsity pattern, so this is the highest number of entries in the column of our system matrix, it becomes higher and higher and higher. And if sparsity is reduced, mumps becomes poorly scalable. So we kind of need more computation time in the end if we go for third order. And there's another reason. And this is also a point that P1 is not completely useless. It is definitely not, because if our model geometry is so complex that we need many, many cells, we are not able to handle this with P2. So if our geometry requires many tetrahedra or many cells, we need to stay with P1 clearly. But if we have a geometry which allows us to go for P2, I would say this is the optimum compromise, and P3 is overkill, and this is also what Octavio and Alexander have written in their publications.
All right, thank you. Alan told me that he wants to make a comment. I think, Alan, you can do that at any time because you have access to your microphone, right?
Yeah, I'll just jump in now, Max, if that's okay.
Yeah, sure. We're still waiting for Q&As.
The one big takeaway for me is something that I learned 20 years ago when Xavier Garcia and I got 4 of the then in use 3D forward codes and compared them. And we were finding 20% differences in the forward codes. Presented this at the 3D EM meeting at Salt Lake City. And that seems to have improved somewhat, but I'm still horrified to see some of these comparisons at the 10% level, you know, and as a field person, we work very hard to get down to 1% data error. And I think a lot of the community are not as aware as they should be of numerical inaccuracies that can bias our models. What would you propose as a way to address this that the community should be working towards?
Oh, that's an interesting question. I think we just need to spend more time and effort and be in benchmarking. So I mean, you know Marion very well, and you know the Dublin comparisons very well. And Marion told me a lot from these comparisons when she was working at LIAC in the beginning when I started. And I know that people spend lots of effort on cross validation, but in the end we spend the effort and we say, oh, it is like it is, and we continue. So that's the problem. And maybe benchmarking solutions is also not no, I'm missing the word. We should be more no, I'm sorry.
Yeah,
I forgot what I want to say.
Yeah, I think we just have to be a little bit careful that you know, with the availability now of codes, and for example, ModEM is used by probably 80% of the academic community. There has to be a better appreciation and understanding of the limitations of each code.
Yeah, I mean, while we're still waiting for Q&A, maybe I chip into this discussion because, yeah, I think you're absolutely right. And sometimes people tend to sort of push things beyond what is sort of reasonable and then sort of get models with strange features. On the positive side, I would say, as somebody who sort of, you know, sits between those groups, I mean, I have made deliberate experiments where I pushed my inversion code to, you know, make really big grids, and, you know, the numerics certainly are on the iffy side. And the good news there is, yes, you get artifacts, you get sort of erratic structures in some parts, but you can sort of identify them. But a lot of the main features, the things where I would say, okay, in either case, I would only be confident in interpreting, you know, this is really resistive, this is really conductive. That stays, yes. And so it's not like all of a sudden you get a complete mess. So there is a degree of robustness. But of course, if we want to move into more quantitative things and really distinguish between, you know, this is 10 ohms and this is, you know, 50 ohms, then all these questions become much more relevant. Yes.
I think within the context of DESMEX, you know, that's mineralized bodies can be extremely complex in their 3D geometry. And if we give a model to a mining company and they drill based on our model and don't find anything, we're in trouble.
Yeah, we are not that happy in that case. Exactly. So I think we just need to continue our comparisons, and now I know what I wanted to say before. We should more acknowledge model comparisons, maybe. So acknowledge publications where people spend time to just compare errors instead of doing something completely new, because it's still an issue. I also agree to you, Max, that modeling errors are not that critical to find the bigger anomalies in our inversion. So this is also what I experienced in the last month in all my tests I did. I can also have a way coarser inversion meshes with coarser receiver refinement. Okay, my chi-square will not be that nice, but the main features will still appear. So, but if I want to have it accurate, I need to spend more and more resources.
Yes. Okay. So it seems like people are still busy typing. I have to think, because when you were talking, there was another sort of question I wanted to ask you, but it sort of escapes me right now. Can you maybe just go back that I can see your little sort of section headers, and then maybe it comes back to me. You know,
section headers.
Yeah. Okay. I think somewhere there. Just okay. There was
modeling or inversion.
Sorry. Okay. One question I got back about this wasn't really what I wanted to ask, but because you were saying, okay, when you showed how custEM is run, you know, you run it with MPI run, but from what you were saying, it seems it's all running on one node. Is that correct? Is there a possibility to sort of distribute? You said you had 2 terabytes of RAM over several nodes, or is it like, do you need one big mega machine?
Actually, I don't know if I understand you correctly. So I have I have also a picture of my workstation I'm using. Wait a moment. It's here. So I run all my simulations on a machine which has 144 cores in total, so 72 physical cores on 4 sockets. So we have 4 sockets with a completely shared memory architecture. So we have 750 gigabytes per socket, and with 4 of them we have 3 terabytes. So this was something that people could buy in, I think, 2070 machine, I think, from Intel. So it's an Intel rack with Xenon Gold processors. And yeah, you need a shared memory architecture. That's basically the point. As long as we require the direct solver mums. If we could have an iterative solver, of course, we can get rid of this RAM problem and be more flexible. That would be great, but I have no idea how to implement it. I think this is more a work for mathematicians, because it's very complicated.
Yes, I mean, of course, those sort of large-scale matrix solvers are, you know, an intricate system where people spend sort of a lot of resources doing this. I was just confused because MPI run, yes, is usually used for MPI programs which are sort of not shared memory. So it seems like you have some sort of hybrid architecture there or something is how it works. But okay, I mean, as a comment, you might look into TensorFlow, because I think they have things like that. And I mean, it is much more than just machine learning. Yes, I mean, everybody knows TensorFlow for neural networks, but I think it's a general matrix framework. So that could be an interesting, at least quick look. Okay, we have a question in the Q&A. Andrea Balzer, would the code comparison done for different CSEM open source codes done in 2021 extend to MT? Can we conclude that the comparison would also have similar results in the MT case?
Oh, I would say yes to both questions. So, I mean, Korea and Menezes did not provide an MT dataset because it's a marine hydrocarbon case. But of course, we can use also MT stations on the sea bottom, if you like. I don't know if there are so many real-world submarine MT applications. Okay, I'm not so familiar with that. So yeah, if that's the case, yeah, one could exchange the CSEM receivers and transmitters with receiver grid of MT stations and do the comparison for the same model. Of course, that would be possible. And I think the misfits between cores would be in a similar error level, because it's what we need in Marlin actually is a resistivity model which is not dependent on this finite difference grid used by Correa and Menezes. So it would be the best comparison would be if we only have seismic constraints and some kind of mathematical function describing the resistivities or something like that, independent of the discretization. But I have no idea how to build something like this, because either you have an FD or an FE or a pointwise discretization.
Well, that's actually okay. That's actually one really interesting point, and something I have sort of run into now as well. I think the solution that you propose, yes, it would make it more, let's say, method agnostic, because as you say, as at the moment it's all geared towards like this rectilinear grids, but I don't think it circumvents the problem, because then all the codes have sort of, you know, a similar problem of turning that mathematical description into a concrete grid, and all the codes will solve it differently. Yes, so you still have differences, but
yep,
the details of that, of course, can matter a lot. Yes, so and I have encountered this, for example, when you take an MT model in a rectilinear grid, but then you go into, you know, geographic coordinates and back. So you take an MT mesh, you go into geographic coordinates, and then you project slightly differently onto like a rectilinear mesh, and you get very much the similar issues. Okay, we have another question from Juan Torrejon. Have you tested custEM with ground TEM coincident or central loop surveys?
Yes, I have. This is the first, so kind of simple setup is the first time domain example in the code repository, and also in the publication of 2021. This is a central loop setup. It has also an out of loop station, so there are only 2 receivers involved, because it's the first kind of proof of concept. But yes, you can have ground-based loop sources with an arbitrary shape and an arbitrary receiver setup, and calculate the transients for all the receiver stations, E field, B field, and B point. So it's all possible.
Okay. At the moment, it seems like nobody has any questions anymore. So thank you very much again. And yeah, I hope, or I assume that, you know, this will also increase uptake of custEM in the community. So probably soon you will get many questions, you know, how to do this, how to do that. I actually,
where is one? Oh,
okay, that was just,
okay.
Thank you for the talk. Yes.
Thank you too for listening.
So yeah, so thank you very much. And everybody else, thank you for attending. And next week we have mining for net zero. So tune in at the same time, if I remember correctly, in 1 week. So have a good day, everybody.
Yep. Bye-bye.